All right, so happy Friday, everybody. Another week down. A couple things before we get going. I need to first apologize. I messed up the syllabus when the other day when Bradley was asking about Veterans Day. I completely botched it. Veterans Day, according to the college, is going to be on actual Veterans Day, which is Wednesday. I have no idea where I read it as we have Monday off. But I don't want to adjust our syllabus. I don't want to adjust what we've got going on in the Canvas. Since we're not actually meeting on campus, it doesn't matter if they're closed or not. So we're going to go ahead and go with what we have on our syllabus and in Canvas, where we will not be meeting on Monday, but we will be meeting on Wednesday. Now, if that's an issue for you individually, please let me know and we will work on arrangements or whatever. I just don't want to start shuffling all the due dates and everything because either I'm going to make a mistake or some of you are going to misread it or something, and that's just going to be more headaches than we need. So I'm just going to admit my error and we're just going to run with it. So again, if that's an issue for you, please let me know. So Ralph, you enjoy the 3-day weekend more. I can appreciate that. Of course, nowadays, the day off, it doesn't really matter because every day is the same. But yeah, I'm with you there. Anyway, so please let me know. So that was the first thing. And then the second thing I wanted to mention is at the end of lecture on Wednesday, I think was the last one, when I talked about circulation, I wrote it wrong on the whiteboard. And the circulation is we're going over a path. So putting the circle on the integral was right, but it's supposed to be F dotted with T, not F dotted with N. So it is a work integral, basically, not a flux integral. So I want to make sure that you guys are aware of that circulation, it's just doing the vector line integral, a work integral, but over a closed path. And we'll definitely do some more of those today. And we'll see what that means when it comes to, say, a conservative field versus a non-conservative field and so on. Okay, so I just want to make sure we got that out
Because
there.
it's T, does that mean that it's going to be tangential to the curve?
Yeah, you're basically looking at what portion of the field is in the direction of that path. And so the reason it's called circulation is, again, think about that field as showing, say, movement of something in water, right? So it's basically saying if we do this path, how much of the fluid is actually flowing in the direction of that path? Hence circulation. So it's tangential. So it is the same as the work integral. And then, so Victor, so positive and negative, yes, that does mean direction. If you get a positive from a circulation, it means that the field is pointing in the direction, overall, pointing in the direction of flow of the path. If you get negative, it's pointing in the opposite direction. So think about, like, if we're talking about currents in the ocean, a positive circulation means the current is helping you move. A negative circulation means that you're pushing against the current. And I said circulation, it doesn't even necessarily have to be a closed loop, but if on a path you calculate your work integral, your vector line integral, and you get a negative, it means that that path is kind of fighting against the current. So that's the difference between plus and minus. And so if you parameterize your curve so you're going the opposite direction, you should get the opposite quantity with your work integral, right? So if you go from point A to point B, going from point B to point A should give you the opposite, the same value, just opposite signs. All right, so that was a good question. Other questions about what we've done up to this point? Other than I know Jacob said he wants to talk a little bit more about flux integrals, and I'll do that before we get to conservative fields. But is there anything else, anything from the homework or anything? Okay, hearing none, I'm going to go ahead and hop up to the whiteboard. So I will see you guys in just 1 second. All right, so let's start with just a real quick review of the different kinds of line integrals. And we'll talk a little bit more about flux integrals since those were the last ones we hit. So in general, line integrals, we're just adding something up over a curve. So we're going to integrate over some curve, our f of x, y, ds. But we saw that a slightly easier way to do this is if we parameterize the curve. So I'm going to write here f of x of t, comma y of t. And then we have times the square root of x prime of t squared plus y prime of t squared dt. Right, so this is the more functional way of doing it, even though the definition is it's just a function with our arc length. So we have to convert from the arc length parameter to the t parameter, plug stuff in and go. So there's our in general line integrals. Then we also had the vector line integrals. And this is the one that I call the work integral. And for this one, we're integrating over a curve. The field dotted with t ds. So in essence, what we're doing is we're finding out how much of a vector field is actually pointing in the direction of our path. But we also saw that the more functional way of doing this is, again, integral from a to b, where we do our function in terms of r. So I'm just going to do it generically, saying take whatever your parameterization is, put it into your field. But this whole square root stuff ends up getting canceled when we use the formula for big T. So all we have to do is we have to take our field, evaluate it at our curve, right, with our parameterization, and then we dot it with the derivative of our vector. So our velocity. Okay, so that was the vector line integral. And like I said, this is the one that gives us circulation. If you do a closed path, I put that, then this is what we call circulation. I don't usually talk about circulation just because it's, well, you're just doing a vector line integral. You just happen to be doing it over a closed path. But because I know it's come up a couple times, when you see circulation, that's all it means. We're doing this, but over a closed loop. And it doesn't have to be a circle, right? It doesn't have to be a circle. It just has to be a closed path that returns to where it started. All right, so that was the vector line integral. And then we also had the flux integral. And the flux integral looks a lot like the work integral. But now, instead of dotting with t, we're dotting with n. Okay, and n is our unit normal vector. So flux, what it is a measure of flow over the curve, through the surface, whatever it happens to be. So the work integral basically tells you how much of that flow is in the direction of the path. The flux integral is saying how much of that flow is across the path, is perpendicular to the path. So you guys are pretty used to now having things that are orthogonal to each other, right? Like big T is pointing in the direction of curve and big N is perpendicular to it. Think of flux as kind of the same idea. It's the orthogonal component to the work. Okay, so what we're looking for is now how much is going through that surface. And I keep talking about going through a surface. Don't think of that surface as a solid barrier or even anything real. We can just imagine any kind of a surface or any kind of a curve. And we'd still be looking at, all right, if there were a surface there that was permeable, how much would be passing through? So flux is always is something that you want to look at when you're curious about how much of whatever is coming by you, coming past you, as opposed to going with you. With you is more the vector line integral.
Will that always be the case? Like, even in an applied sense, the work done on an object, the flux through that object will always be orthogonal to the work?
Well, it's basically the result isn't necessarily orthogonal because the result is a number, right? But what we're adding up are the orthogonal pieces. Because think about what an integral is doing, right? It's adding up a whole bunch of chunks. This one, the work integral, is finding the component of the vector, of the field vector, that points in the direction of travel. I don't know, you remember the term projection of a vector? This is the projection of a vector onto the tangent piece. This is the projection of the vector onto the normal piece, on the orthogonal piece. So we are adding up the orthogonal chunks. Always. The result, though, is going to be just a number. And to say that two numbers are orthogonal don't really make sense. I mean, you can tweak orthogonal to make it work, but I think you see what I mean.
Yeah, thank you.
Yeah, you're
Is
welcome.
there an easier shortcut for finding the normal vector for problems like these? Because on the quiz we just took, even that like really simple R of t like led to some like a really painful looking normal vector, and I was wondering if there was any sort of quicker way to find that, or I don't know.
Yep, there absolutely is. There absolutely is. So the more practical way of doing this, while this is the actual definition, the more practical way we do this is to integrate from A to B, F dotted with this guy little n. And if R is, let's call it, no, we'll call it x of t, y of t. Right, so then R prime is x prime of t, y prime of t. We define n as y prime of t comma negative x prime of t.
Right.
I
remember that from yesterday.
Yeah. And when you have a line integral is two-dimensional. You can make it two-dimensional. We can bring it back to a two-dimensional case. And if we can do that, if we can make it, if it's two-dimensional, this is the fast, easy way of doing it. Right. And I think Seamus, when you and I were talking maybe yesterday, you asked me about how do you know which one's negative? And I was like, well, it's always the second one. You're like, always? I'm like, yeah, always the second one. The deal with flux is that which direction is positive and which direction is negative is arbitrary. Just like if I go up, is that positive in y? Or is down positive in y?
I don't know.
The answer actually is, it depends how we decide to set it up. You have seen circumstances where up is positive and also circumstances where down is positive. think anytime when we were doing things like fluid pressures and stuff like that, we often went with down being positive. So you can decide plus or minus however you want. And so if we do it this way, just so you know, if we do it this way always, if you're on a curve that's got this, say, this orientation, then plus is in this direction. It's to the right as you're going along the curve. If you have flux going the other way, that's minus. So we're going to just always go with it this way because, well, pick your favorite way. But if you do it this way, positive flux means there's more flow going towards the right on this path. So like, let's say we had a circle, our good old unit circle that we're kind of used to and going around in a counterclockwise direction. So if we were to calculate flux over this and get a positive, that tells us there's more flow going outward. Because outward is to the right, this orientation. If we got a negative flux, that would say more is coming inward. All right. So for those of you that are in physics right now, really just think that the difference would be like a charge, right? Plus versus a minus. That's just going to change which direction you're going, right? Change your flux. But in physics, how do you decide which direction you're going, like in electrical?
Depend on the charge.
Yeah, it's the charge. And so negative charge is what we use as the standard when you're doing electric fields, right? But in math, since it totally doesn't matter, we're just going to go, all right, this is what we call positive orientation of a curve. It's positively oriented if on a loop if we're going in a counterclockwise direction. It's just how we define positive, because you got to have some way of saying positive or negative. So this would be a positively defined curve. If we went the other direction, it would be negatively defined. But if you don't have a loop, it's awfully hard to tell whether you're positive or negative, right? Like this one. So that's why we just say, all right, we're going to make it standard that positive is to the right, which kind of makes sense, right? When you think about like the real number line and stuff like that. Anyway, so to get to Jacob's question, right? The point is, yeah, it can be way faster. And that was the intention of that one on the quiz. But if it's not two-dimensional and you have to do the 3D thing, then yeah, you just got to slug it out.
Oh, is there going to be something like that on the next exam?
Like 5 of them, yeah.
Yeah, okay.
Yeah, at least 5. Probably more like 10. Which is completely facetious, right? Yeah, no. Will I give you one? I don't know. I mean, I haven't written it, obviously. But my intention is whatever I give you, the end should be fairly nice. Like, and the one thing I'm going to always remind you, think about simplifying. Because a lot of times if you simplify it, especially if we've got some trig action, can make those things a lot easier. Okay, so don't forget about things like sine squared plus cosine squared. Don't forget about things like square roots of squares and stuff like that. Anyway, so is that kind of what you were looking for, Jacob? Was that?
Yeah, that's perfect. That's perfect.
Okay, cool. All right. Well, you're going to like today, or at least you're going to like the result of today. You're going to be a little bit mad at me that I didn't share this earlier, but I got thick skin. I can deal with that. But what I'm going to show you is what's really nice about conservative vector fields. So let's remind ourselves about those. So what does it mean if a vector field is conservative? All right, so Victor just put, it has a potential function. Good. That's one of the important things to remember is that there is a potential function. And what is the potential function? Like what's special about it?
It's the gradient of the vector field.
Okay, so other way around. The field is the gradient of the potential function. But you remember gradient, which is also really important. So when we have conservative vector fields, that just means that there is a function so there's a function f such that the gradient of f is the field. All right, so that's kind of the important thing to remember about conservative vector fields. And this guy f, this is the one that's called the potential function. All right, so hopefully you remember how to find the potential function. Had to do that on your quiz as well, right? We just do partial integrals of the different pieces and then kind of stick it together. And hopefully you also remember how to check if you've got a potential function. Do you remember how to tell if a field is conservative?
You don't get zero, right? Something like that.
The zero is involved somewhere.
Zero is involved somewhere. Yeah, kind of. The check I'm suggesting has to do with partials. Let me show you if it's a three-dimensional, we'll go with the generic.
Yeah. The m sub y has to equal n sub x.
Yeah, so if we have, and I'm pretty sure the book does MNP. No, yeah, PQR. Crap. I forget, which one does the book do? I think they do PQR. I don't know. I'm going this way. To hell with the book. All right, so if this is F, we know it's conservative if, and I'm going to put here, and only if, meaning if what we just write here is true, then it must be conservative, like it goes backwards. But we've got my has to equal nx. Also, mz has to equal px. And also, nz has to equal py. And I apologize if p, q, and r are m, n, and p, but just shift the letters. Okay, so we have a way to check if it's conservative, and it just comes to looking at all these different partials. Right? All right, now here's why we like conservative vector fields.
I have a quick question for you.
Yep, go for it.
I'm lost. I'm confused now. If I have a vector field,
yep,
and I take the partial derivatives of the whole thing, that gives me the potential function, correct?
You take the partial integrals,
Integrals.
you get the potential function.
Okay.
Yep.
And then if I have the potential function and I take the partial derivatives of that, I get the field. Right?
Correct. Yes.
Okay.
Correct.
Shit. All right.
Did you just realize you went the wrong way on the quiz?
Yes, I did.
All right. Hey, these things happen, right? Okay, so here's why we care about conservative vector fields. All right, so I'm going to give you a list of a couple of things that are true if we've got a conservative vector field. We'll kind of prove these as we later, but let me just give you the list. So first of all, the path doesn't affect the vector line integral. Only the start and end matter. Okay, so vector line integral, that's our good old work integral. And it doesn't actually matter what path you take going from point A to point B. All that matters is you went from point A to point B. So you may remember the very first vector line integral we did, and we took like 3 different paths and we got the same value every time. I think it was 0 every time. Well, that was because we were using a conservative vector field. I think that was the one that was yx, right? And then we changed it to y minus x, and we saw that we didn't get the same thing every time, right? Well, yeah, that's because it was non-conservative. So here's the first thing. That's huge. This is great, because if you can recognize that it's conservative, take the easiest path. Whatever easy is, take the easy path, because it's just as good as any other path. All right, so there's the first thing that's really kind of nice. The second thing, and this is super, super useful, is that if the path is a simple closed path, I'll explain those words in a second, the vector line integral will be 0. All right, so before we move on to third thing, this simple closed path, what does that mean? All right, well, closed should make sense. What is a closed path?
A shape, not
Yeah, shape is
a two-dimensional object. I don't know, three-dimensional object.
Something
I think
a lot.
like a shape, not a line.
It doesn't have a beginning nor an end.
Yeah, there is no beginning or end. It comes back to itself, like a circle. Victor put in the chat box. A circle is a great example. All right, a closed path. So here is a closed path. Here is a non-closed path. Ooh. All right. How about this one? Closed or not closed?
Not closed.
Not closed. Even though it's got a loop, it's not closed because there still are kind of endpoints. If I were to erase those, now it's closed.
Wait, so is an ellipse a closed path?
An ellipse is a closed path. A square is a closed path. Any polygon is a closed path, right? So those would all be closed paths. An infinity symbol is a closed path. Yeah, you buy that?
Yes.
Yeah.
Right, even though it's got 2 loops, it's still closed because there is no beginning and there is no end. Okay, so that's what it means to be closed. That's, I think most people it's pretty obvious what that means, so we're good with it. So then the question is, what about simple? Okay, so we got some closed paths up here. Some of them are simple and some of them are not. These 2 that are in blue are simple. This infinity symbol, the red one, is not simple. Okay. So a simple path, what that means, a simple closed path, means that the region that lies within it is only one piece, and one piece without holes. All right, so you think about this one, if you think about the region that's contained within it, there are actually two pieces to it. So it's not, we say that it's not simply connected. The region is not simply connected. So its boundary is not simple. This one, if you look at its interior, is just one nice big chunk. So this one is simply connected. So therefore, its boundary is a simple curve. All right, so kind of makes sense what a simple closed path is?
Yeah.
Yeah. We're feeling okay with it? Okay. So
what would a
if your
complex closed path be, though?
So it's not simple. It's not complex. It's just not simple. And there's an example of one.
Okay.
Or here's another one. Think of the boundary to this shape. Seeing it's been Halloween and all. All right, so think about that region. So the piece that's interior to it, this is when I wish I had an orange pen. That's not simply connected because of the fact that there are holes in it. So this curve, and this is where it gets kind of weird because this curve has multiple pieces, right? It's got the circle, it's got the two triangles as eyes, and then I don't know how many sides it has. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's a nonagon. Those all together form a curve, but it is not simply, it's not a simple curve. It's closed, but it's not simply closed. So this is the kind of thing you get when it's not simple, which now you're starting to see why it makes sense to call this just a simple curve, simple closed curve. It's not very creative. It's just, yeah, we go around the loop one time and we're back to where we started. So that's a simply connected region with a simply connected or a simple closed path boundary. Getting tongue-tied. All right, so basically, these are going to be all the nice little paths that you know of where we start here and we end here. But if we do things like we go around twice, we cross our path somewhere, things can start getting affected then. But we're guaranteed that if it's a simple closed path, then the vector line integral is going to be 0. All right, so there was number 2. Well, that's great and all. But number 3 is the one that you really like. Here comes number 3. Number 3 says that if the curve starts at A, at the point A, and ends at the point B, so I'm just going to label the points A and B. We're not going to worry about their coordinates. Then the integral over this curve of f dotted with TDS is equal to f of B minus f of A, where B and A are the starting and ending points, and this little guy f is the potential function. So that probably looks a little familiar. What do you know that as? You've seen something a lot like this before. Where'd you see that before?
A work integral, right? Or
Okay, so this is the work integral, but the fact that the integral is equal to, say, f of b minus f of a.
yeah, that's a fundamental theorem.
So Victor just threw that. Yeah, that's the fundamental theorem. So you know the fundamental theorem for just regular old integrals. Well, this is the fundamental theorem for line integrals. And this is awesome. This is so awesome. You're going to love this. But remember, it only works for conservative fields. Okay, if your field's not conservative, we cannot do this. All right, now I want to show you that actually 1 and 2 are actually consequences of this third one. They're actually just things that happen from the fundamental theorem. Because think about this, the closed path one. If we start and end at the same point, what does the fundamental theorem say is going to happen?
0.
You're going to get 0, because if a and b are equal, then f of a and f of b are equal. We get 0. Well, think about the first, that the path itself doesn't matter. Well, isn't that what the fundamental theorem says? All that matters is where we start and where we end, not how we get there. All right, so the fundamental theorem of line integrals, that should actually just been number 1. And then these other 2 things wouldn't even been on the list. But I wanted to share those because those are going to be kind of useful just in general. This first one can be really useful, especially when trying to find the potential function is difficult. If it's easier just to go, hey, let's just take, say, the line that connects A and B and do it, instead of whatever weird path you give me. This second one, that's one of those where you just go, oh, closed loop, done, 0, since it's a conservative field. Okay, so let me show you how this works. And we're actually going to go back and revisit that one that we started with way back when, where we had our field was y comma x. And we were going from the point 1, 0 to the point 0, 1. So let me show you how we could have attacked this without actually doing a line integral. So first things first, we want to show that this thing is conservative. So if we call these guys m and n, we need to look at my, and we got to look at nx. Okay, well, my is 1, nx is 1. Since those are equal, we know that this is conservative. And you get very happy when you see that it's conservative. Because now we can actually do the fundamental theorem. So let's find the potential function. So we need to integrate y with respect to x. And that gives us xy. If we integrate x with respect to y, we get xy. So that means that our potential function is xy. Take its gradient, and you'll see that we get this vector field. Okay, so now let's use the fundamental theorem of line integrals. So A is the point 1, 0. It's where we're starting. So if we plug 1, 0 into the potential function, we get 1 times 0, which is 0. point B is 0, 1. We plug that into the potential function. We get 0 times 1, which is 0. So what we know then from the fundamental theorem is that if we go over this curve, this work integral is going to be 0 minus 0, which is 0. And it's independent of path. It doesn't matter which way we go. So you may remember we did this 3 different paths. We went on the circle, we went straight, and then we did the old, let's go through the origin. So we're doing the sides of the triangle. But in each of those, we ended up getting a value of 0 when we did the integral. But if you go back and you look at what we actually had to do those line integrals, this is so much faster. Oh my God, it's faster. Okay, so we want to check for conservative, because if we got it, it's a snap.
Are electric and magnetic fields conservative? I don't remember.
Okay, so are magnetic fields conservative? You're taxing my memory, actually. I don't know if all of them are conservative. I do know that gravitational fields are conservative. I know that magnetic fields of point charges are conservative. I don't know about like if you extend it to like a bar magnet or something like that. Same thing is true with electrical fields. If it's just a point charge, it's conservative. If it's an extended object, I'm not sure. I don't remember.
I think it wouldn't be, because that makes sense.
Yeah.
That it wouldn't be.
But I know for sure that if it's just a point charge, like if you're looking at the electric field created by an electron, that is conservative. All right, so be on the lookout for conservative vector fields, because when you've got them, oh my God, they're easy. Now you don't care what the path was. You really only care about where did we start and where we end. So if you can get the potential function easily, you can just dive right in with the fundamental theorem. And even if it's not easy to find the potential function, if there's a path that makes it really easy to calculate from one place to the other, you can just do that integral and be done with it. Right? Like, for example, let's take the same field, just so we know we've got a conservative field. But what if the path was this? We're going to go from 1, 0, but we're going to come up here, do like and then do a semicircle to this point. Okay, so this is our path. Even if I don't have a way of getting the potential function, which I know I already know it is pretty easy. Instead of doing this weird, crazy path, what I could do is just do the linear path right here. And check out how fast this one is. Let me just say that this is the point, let's say 3, 0. Let me show you how easy this one is to set up. So we need to parameterize this red path. Well, the y is always 0. And the x is, well, how about t? And this is going to be t going from 1 to 3. All right, so that makes my field 0t, right? Y comma x. I need r prime. That's 1, 0. So my integral is going to be from 1 to 3 of these two guys dotted together. And this was probably just as fast as finding the potential function. And talk about an easy dot product. That thing just dots to 0, and I got 0 again. Well, you can see why we're going to get 0 if you look at the fundamental theorem. Since the potential function was xy, and the y coordinates are always 0, I'm going to get 0 minus 0 again. But hopefully you kind of see my point I was making here, where I didn't find the potential function. I mean, we did, but we didn't. But using just that like linear path, the parameterization was fast and easy. So getting the pieces we needed to do the line integral was quick. So conservative vector fields are your friend. Look for them. That should be the first thing you always check anytime you're doing any kind of a line integral with a field. Is it conservative? Because if it's conservative, oh, hell yeah. All right, now I notice that we're out of time, and I haven't proved this to you. And you know that's not good enough for me. So what we're going to do on Wednesday, after we talk questions about homework and all that, I want to prove to you the fundamental theorem. I want you to see where it comes from and why it is. So you have a little bit better appreciation of it. And then we'll probably do a couple more examples. But then we'll start going to the, all right, but then what if it's not conservative? Are there still some maybe faster ways of doing some of these integrals? And the answer is yes. We're going to develop some other theorems. There are a whole bunch of theorems that we're going to do. The next one's called Green's theorem, not named after Larry, he wishes. But we're going to do Green's theorem, which will allow us to do closed loops on non-conservative fields. There's actually a much faster way of doing those. But that's where we're going to go next time. All right. So with that, I'm going to go ahead and stop the recording and wish you guys all a great long weekend.
Are we going to have a